this is problem number 2. Given this sequence, write an equation for the nth term. So in this pattern, we first need to notice that we're increasing by 8. And when we're writing the equation, we can say t of n equals, or you can use the notation a sub n equals. We need to include the initial value, which would be the 0 term, the term before -5. So if we're adding 8 to get to the initial value, we need to subtract 8. So that would be -13. And then we're adding 8 each time, so plus 8n. Find a sub 22 of the sequence. So in other words, find the 22nd term. The fastest way would be to use this explicit equation and plug in n equals 22. So we do 22 times 8 and then minus 13, and we get 163. So the equation we wrote here was an explicit equation. The equation in part C is a recursive definition. So recursive definition has two parts. One is stating a term, so we can state the first term, which is -5. The recursive definition tells us how to find the next term. So to find t of n, we're writing how to get the next term from the term before it. So the term before it would be t of n minus 1, and we're adding 8 to the term before, so plus 8. So both of these together are the recursive definition. On number 3, we're considering this recursive definition that's given, and we're trying to find t of 4, or the fourth term. So this recursive definition is telling us that to get the next term, we take the term before it, t of n minus 1, and then subtract 7. So if we know that the first term is 10, to get the next term, we take 10 and subtract 7, so 3. But we need the fourth term, so I'm going to keep going till I get to the fourth term. So keep subtracting 7 from the previous term, and we end up with the fourth term being -11. So now if we're writing an explicit equation for that same sequence, t of n equals, we need the initial value. So we have the first term is 10, but the initial value would be the term before it. So we need to add 7, so that'd be 17. And we are subtracting 7 each time, so minus 7n.